Hi everybody. So in this video we're going to continue with Chapter 7, Statistics, and now we're going to go into Section 7.3, Measures of Variability. First we are going to talk about range. So the range in a data set is a difference between the largest and smallest observations. So consider the expenses data given in Table 7.1. Also consider the same data with the largest value of 68 replaced by 120. What is the range for these two sets of data? So the expenses data was that table where they were talking about weekly expenses for university students. And the maximum was 68 and then minimum was 38. Therefore, the difference will be 30. And that is the range. And here on the right-hand side of the table, we have expenses data with an outlier. So 120 would be an outlier because it is pretty distant from the rest of the data. And this would affect the range because 120 minus 38 is 82. Therefore, we have a much larger range with an outlier. So in the next slide, we're going to find a reference to variance and standard deviation. So variance. The sample variance, which is symbolized with s squared, is equal to the sum of the squared differences between each observation, so that would be x sub I here, and the sample mean, divided by the sample size minus 1. So if we had to do this manually, we would have to subtract each observation from the sample mean, then square that, add them all up, and divide it by the sample size minus 1. Then we have the population variance, which is sigma squared, and that is going to equal the observation, the difference between the observation and the population mean squared. So we add all these and then divide by the population size n. So basically it's the same formula, except that we don't subtract 1 from the total population. The standard deviation is simply the square root of the variance. So in this case, this is the variance for the sample, and we square rooted it. And this is what's called the standard deviation. For the population, it would be the same thing. If you want the standard deviation of the population, all we would have to do is square root the variance of the population. Now, these measures of variation are about the mean, as we said. And if we get that the standard deviation is equal to 0, it means that all the data is on the same value, and there's no variability about the mean. If the standard deviation is large, then that means that there's a large amount of variability about the mean. So consider the following example. In business, investors invest their money in stocks whose prices fluctuate with market conditions. Stocks are considered risky if they have high fluctuations. Table 10.5 shows closing prices of two stocks traded on Vienna's stock market for the first 7 business days in September 2017. Even though the two stocks have similar central values, they do behave differently. It is obvious that stock B is more variable, and it becomes more obvious when we calculate the standard deviations. So if we look at stock A, we can notice that it has apparently less variation than stock B. So they give us the mean, which in both cases is 5. We're going to need the mean to calculate the variances. So for stock A, we do the difference of the observation and the mean and then square it, right? Notice that we do the same thing for each observation. Add them up and then divide them by the sample size. Now, I know that before we said that for the standard deviation of a sample, we should subtract by 1, but normally they don't do it. So once we do all that, for the case of stock A, the variance would be 0.464. Then we repeat the same process for stock B. Again, getting each sample, subtracting it from the mean and squaring it. Adding all those different samples up and then dividing by the sample size. And for stock B, we get a variance of 8.21. Then we simply square root them And we get that the standard deviations would be for stock A, 0.681, and for stock B, 2.865. So that means that stock B is 4.2 times as variable as stock A. So next we have the interquartile range and measures of non-central tendency. So let's talk about percentiles and quartiles. So the first thing is that the data must be in ascending order. So you would have to put all, if you did this manually, you would have to put all the data in ascending order. Percentiles separate large order data into sets of hundredths. So the pth percentile is a number such that p% of the observations are at or below that number. Quartiles, on the other hand, are descriptive measures that separate large ordered data sets into 4 quarters. So the first quartile, Q1, is just another name for the 25th percentile. 25% of the observations are at or below the value of the first quartile. So you can find it by simply multiplying n plus 1, so the amount of data plus 1 times 0.25, or if you prefer, n plus 1 divided by 4. And this is if it's ordered. The third quartile would be 75% of the observations, and it is calculated by multiplying 3 times n plus 1 over 4, or 0.75 times n plus 1. The median is going to be the 50th percentile, also known as the second quartile, or Q2. So a measure that helps to measure variability and is not affected by extreme values is the interquartile range. It avoids the problem of extreme values by just looking at the range of the middle 50% of the data. So that's, by the way, the interquartile range, also known as IQR, is going to equal the third quartile minus the first quartile. So talking a little bit more about the interquartile range, measures the spread of the middle 50% of the data. It is the difference between the observations at the 25th and at the 75th percentiles, or like I said before, quartile 3 minus quartile 1. So if we consider the student data in table 10.2, and once again look at that same data with the outlier 120 replacing the largest value 68, we would have the following results. So we're talking about the expenses. The minimum was 38 and the maximum was 68, and then the median was 55. The first quartile would be 50. The second quartile is the same as the median. The third quartile would be 61. Then here the range is 30. And the IQR is going to be 11, right? It's just subtracting quartile 3 minus quartile 1. Now, the expenses with the outlier, notice that now the maximum is 120, the minimum is still 38, but now the range is larger, it's 82. But using the quartiles prevents this outlier, 120, to affect the first quartile, the median, or the third quartile. And that means that the range doesn't take into account how the data is distributed, and it is of course affected by extreme values. However, the IQR evidently does not have that problem as we just stated. So next we have the term 5-number summary, and that just refers to the 5 descriptive measures: minimum, first quartile, median, third quartile, and the maximum. So 1, 2, 3, 4, 5, the 5-number summary. Then we have a box and whisker plot. And that's when we have the 5-number summary, and you can put the information together in one graphical display called the box plot, also known as the box and whisker plot, which is what we're going to see next. So the first thing you would do is draw an axis spanning the range of the data, mark the numbers corresponding to the median, minimum, maximum, and the lower and upper quartiles. So 38 is a minimum, as we can see here. 68 is a maximum. The first quartile is at 50. The third quartile is at 61. And the median is 55. Then it says draw a rectangle with the lower end at quartile 1 and the upper end at quartile 3. So that's this rectangle that we see here. We would draw this rectangle. And then notice again that this would be the median. To help us consider outliers, mark the points corresponding to the lower and upper fences. Mark them with a dashed line since they are not part of the box. The fences are constructed at the following positions. So lower fence would be first quartile minus 1.5 times the IQR. And the IQR, the interquartile range, would be 61 minus 50 or 11. So that's why for the lower fence we would go 50 minus 1.5 times 11, which would give us 33.5. So that's what you see here, 33.5, the lower fence. Then for the upper fence, we would add that 1.5 times the IQR to the third quartile. So we would get 61 plus 1.5 times 11, and that's 77.5, which we can see here. Then it says mark any outlier with an asterisk on the graph. You can see the asterisks there. Then it says extend horizontal lines called whiskers from the ends of the box to the smallest and largest observations that are not outliers. So this is the horizontal line, and this horizontal line, and this other line there, the vertical one, and we would have those two whiskers. So here you see a box and whisker plot of the same information, but this time created by a software package called Minitab. Then what you can see is that this box here contains 50% of the data. The width of the box is the IQR, remember. So this would be the IQR, the width of the box. And that tells us that about 50% of the student's expenses is 11 euros, which seems reasonable if you look at the spread of the distribution. And we can see that in the histogram below. So next we have an ogive, or a cumulative frequency chart. So notice that we have the value 40, which is about half, because the total frequency is 80. In other words, there's 80 students. So half of that would be 40 students, and then 1/4 of that would be 20 students, and 3/4 of that would be 60 students. So that means that this 20 would help you find the first quartile, which is around 50, the median, which is around 55, and the third quartile, which is a little bit above 60. So in the next slide, you're going to find a table where there is an estimation of the mean and the variance. So the first thing they did was take the midpoint of each class. Notice that there's a midpoint of each class. So this right here is a big assumption, because this means that they're assuming that all the data between, say, 60 and 65 is going to be 62.5. But there's no other way to do it except by some kind of approach of this sort. So then we would have the midpoint, as I said, and next to that, the number of students, or the frequency, right? So this would be the frequency, the number of students for each set of living expenses. Sum them up and you get 80 students. Then we would find the mean by multiplying the midpoint times the frequency, or the number of students. So we get these numbers here. We add them up and we get 4,485. Divide that by 80, which is the number of students, and we get 56.6, which is an approximation to the mean. Then, in order to find the variance, we would subtract each midpoint from the mean and square that. So we would get this. Then we would have to multiply that by the frequency, and we would get this. Add them all up, and we're going to get 4,509.6. So we have to divide that by the sample size, which is 80, and we're going to get a variance of 56.37. Square root that, and the standard deviation would be 7.51. Okay, so next we have example 7.8, and it says speed limits in some European cities are set to 50 kilometers per hour. Drivers in various cities react to such limits differently. A study was undertaken to compare drivers' behavior in Brussels, Vienna, and Stockholm. The table shows the recorded speeds of different drivers. Use box plots to compare the results. Okay, so in order to do this, we're going to use the graphing display calculator, but as an illustration of what this process is like, I am going to do it manually for the city of Brussels. So the first thing you want to do is put the data in ascending order. Next, you want to count how many data points you have. That's going to be n. Okay, now we're going to find the first quartile. And remember that the formula is simply n plus 1 divided by 4. It's going to be 17 divided by 4, and this is equal to 4.25. So that means that the first quartile is between the data point 4 and 5. So we would count 1, 2, 3, 4, 5. So that means that this would be the first quartile, 46. Okay, for the second quartile, it's the same as finding the median. So it would be n plus 1 divided by 2. So this would be 17 divided by 2. And this is going to equal 8.5. Okay, so that means that the second quartile, or the median, would be between the 8th and 9th data point. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9. So between 49 and 51, so that means 50. Then for the third quartile, remember that it's going to be 3 times n plus 1 divided by 4. And this is going to be 3 times 17 divided by 4, and this is 51/4, which is equal to 12.75. So that means that the third quartile is between the 12th and the 13th data point. So we count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that would be between 60 and 61. So 60.5 would be the point of the third quartile. So this, together with the maximum and minimum values, would be what we need to draw the box and whisker plot. But let's go to the GDC. First, we go to Stats again, and then Edit. And notice that in List 1, I already have all the data for the city of Vienna. In List 2, I have the data for the city of Brussels. And in List 3, I have the data for the city of Stockholm. Now, I have not worried about frequencies. I've just typed in the raw data. The calculator will do all the calculations with the frequency and all that, so that's wonderful. Then what I have to do is go to Second and Stat Plot. And let's go to Stat Plot 1, and here I have to make sure it's on. Then I choose the type, which in this case would be this one, the box and whisker plot. And then we have that the X list would be 1, and here we have to type in frequency 1. Okay, then let's go to Plot 2. Let's go up, scroll up, and go to Plot 2. Enter, make sure it's on, then choose the right type of graph, again, box and whisker. Then the X list in this case is going to be list 2, again, frequency of 1, and we use a different color, red. So this would be for Brussels. And then let's go to plot 3. Up to plot 3, hit enter there, and then it has to be on. Then we would have to go and choose again the box and whisker plot. The X list is going to be list 3, which is the information from Stockholm, and then again a frequency of 1. Then we're going to go to zoom, and we're going to click on number 9, zoom stat. So notice that the blue box and whisker plot represents the data for the city of Vienna. The red one is Brussels, and the black one is Stockholm. So from this, we can draw some conclusions. So notice that the drivers in the cities of Vienna, which is blue, and Brussels, which is red, tend to go a little bit faster, or actually quite faster, than the drivers in the city of Stockholm. So for Vienna, The median is 51. So that means that about 50% of the people respect the speed limit. But then as you go towards the right, you can see that there's 50% that go above the speed limit because you have the third quartile at 59.5 and the maximum at 63 kilometers per hour for the city of Vienna. And then if you go to Brussels, the median is 50 kilometers per hour, so half the population respects the speed limit. The third quartile is 60.5 kilometers per hour, and the maximum is 65. In the city of Stockholm, the maximum velocity is 51 kilometers per hour. For the third quartile, we have 47.5 kilometers per hour. 75% of the people drive less than that speed. And then the median is 38 kilometers per hour.